Good morning, students. In the previous lecture, we discussed about analog to digital conversion, and we discussed about the two parameters, which are sampling time and the quantization. More in detail, we discussed the sampling time and how it determines the quality of the reconstructor signal. The sampling time is related to the sampling frequency Fs. Fs is equal to 1 over Ts. And in order we have a better signal when we do the reconstruction means when we are changing from digital to analog, we have to sample with a sampling frequency Fs, which is greater than or equal to the maximum frequency of the analog signal. This is called Nyquist criteria. And we said that if we want to have a better signal, the sampling time should be smaller. However, when we have smaller sampling time, we need a lot of memory to store the data. And when we make the sampling time large, then when we do the reconstruction, we will not have a perfect signal or during the reconstruction. During the reconstruction, we will not have the quality that we want from the reconstructor signal. So the sampling time determines the analog to digital conversion and digital to analog conversion process. Today we will study about quantization. Okay, what is quantization means? Okay, first when we do from analog to digital conversion, we sample it. When we sample it, the signal was originally continuous in time and continuous in amplitude. So it will be changed to discrete in time but continuous in amplitude, meaning the amplitude can be any value. Then this is the first step, which is called sampling. Then we have to again discretize the continuous values. So changing from continuous value to discrete value is called quantization. Okay, so quantization means we will have a set of values and we need to map the sampled analog signal to a certain set of values. When we do, after that, we have to change it to binary to have the bits. And here I start with binary number representation because it's related to analog to digital conversion. After discrete in value, we change it to binary. So let's refresh our previous lecture about binary number representation. The conversion from the sample value to bits is done by the quantizer. A quantizer is a device that converts analog or continuous value sample, for example XA, into discrete value or quantized value XQ. For example, if I have labels like 0, 1, 2, 3, 4, 5, 6, 7, these are 8 labels. And if the analog signal is, for example, 2.5, or 2.6, the next level is 3. So I quantize it to 3. That means, so changing the value 2.6 to 3 is called quantization. So since computers express numbers as a set of bits, after the quantization, we have a binary number, changing the discrete value to binary. So this is a binary number representation. If I have a binary number bk minus 1, b2, b0, that means k bits. So its decimal representation is given by this, you know this. D is bk times 2 power of k plus bk minus 1 times 2 power of k minus 1 until plus b0 to power of 0. For example, if I have 1011, this is in binary 2. Let's change it to decimal. 1 times this position is 2 power of 3. Okay, so 1 times 2 power of 3 means 8, plus 0 times 2 power of 2, which is 4, plus 1 times 2, plus 1 times 1. So the number will become 11, the decimal number. So one method of converting decimal to binary is by repeated division, and by successive division, and by recording the remainders until the last quotient is 0. The remainder yielded from the division provides the sequence of converted bits beginning from the least significant bit P0. So let's see this with an example. So for example, I have here 53. Okay, this is decimal, so we want to change it to binary. So we do successive division. We divide by 2, and then we record the quotient and the remainder. So 53 divided by 2, the quotient is 26, and the remainder is 1. And 26 next, 26 divided by 2, the quotient is 13, and the remainder is 0 because 13 times 2 is 26. 13 divided by 2, the quotient is 6, and the remainder is 1. 6 divided by 2, the quotient is 3, the remainder is 0. 3 divided by 2, the quotient is 1, the remainder is 1, and lastly 1 divided by 2, the quotient is 0, and the remainder is 1. So we record all these remainders. And the last one is the most significant bit. That means B5. B5 is 1, B4 1, B3 is 0, B2 is 1, B1 is 0, and B0 is 1. So we start from the last and we collect all the bits, ones and zeros. And that will be the conversion from decimal to binary. So 53 base 10, and in binary it will be 110101, 110101. Okay, by this way we can change any decimal number to binary. Okay, any decimal integer can be expressed in binary. Since the sample values of analog signals do not necessarily produce integer values, we need a quantizer that converts the actual value to an integer. Because if when we sample, the sampled value can be, it is continuous in value and it can be decimal. For example, if it is 5.4, 5.4 or 5.6 or 7.4, these are decimal values, having decimal digits. So in that case, we need to change it to integer. We need to change it to integer because the quantizer have a certain discrete values, integer discrete values. A staircase pattern of value is the easiest way of, the simplest quantizer is a staircase pattern. We will see it in the next slide. The quantizer generates a staircase pattern of values with quantization step delta. Delta at the beginning of each sample period is. Each step in the quantizer staircase is given a binary designation to encode a quantized value, which is a quantized value which has a corresponding set of bits. We will see this. For example, I have here, this is the starting level. So this is a quantizer, the quantizer of 4 bits. 4 bits. For 4 bits, how many possibilities I have? 2 power of 4, 16. I will have 16 different values. So if I start from 0, for example, 4 zeros, and the last one will be 4 ones. 4 zeros, and the last one will be 4 1 means 1 1 1 1, 15. So using 4-bit, I can go from integer value 0 to 15. The last will be 15. So each step is here. For the first step is 0 0 0, and the next quantization step is 0 0 1, which refers to 1. The next is 0 0 1 0, which refers to 2. 0 0 1 1 refers to 3, 4, 5, and so on. So this is, as you see, it looks like staircase. So we say this staircase quantization. Okay, quantization is a staircase. Now, if we sample analog signal, how we can associate it to a certain quantized value. For example, I have here a certain analog signal, and at this point, I have this value. This value is, for example, between 0 and 01 means 5, okay? And the next value is 6. This value is somewhere between 5 and 6, okay? This is the analog value, for example, at time step 1. It can be at 1 second. So if at 1 second I get a value between 5 and 6, I will quantize it to the next value. What is the next value? 6. So any value between 5 and 6 will be quantized to 6. And another one here is if I have another at time t is equal to 2, if I have a sampled value between 10 and 11, then I will quantize it to 11. 11 means 10111 bits. Okay. By this way, we quantize any continuous value to discrete value. That's what it means. Okay. If I have any value between 9 and 10, then I will quantize it to the next level. What is the next level is 10. So if I have any continuous value between 9 and 10, it will be, after it comes out from the quantization, it will be, as a quantizer, it will be 10. So the quantizer can be characterized by the number of bits, okay? The number of bits and its range, which extends from the minimum value to the maximum value. And the number of steps for the quantizer is 2 power of b. For example, if I have a 4-bit quantizer, how many steps I have? 2 power of 4 is 16. The first step is the minimum value of the analog signal, V min. And the last step, the maximum value is the minimum one plus 2 power of b minus 1 times delta. Delta is the quantization step. Okay? One more thing, when we do quantization, remember, for example, if I have a value of 10.6, when it comes out of the quantizer, 10.6 will be 11. But if we approximate 10.6 to 11, that means we are making error. So the error due to this approximation is called quantization error or quantization noise. So we call it quantization error or quantization noise. And this will affect the reconstructed signal. Okay. Now let's take an example. Let's have a 4-bit quantizer. So 4-bit, and let's have analog value 0.44 volt. And the quantization step is 0.1 volt. Okay, delta. And the minimum value is 0. So what will be the maximum? The maximum is the minimum plus 2 power of b minus 1 times delta. The minimum is 0. And plus 15. 15 is 2 power of 4 minus 1 times delta. Delta is 0.1. So it will be 1.5. So that means all values be, from 0 until 1.5. So 0, the next one 0.1, the next one 0.2, the next one 0.3, the next one 0.4, 0.5, 0.6, and so on, and finally 1.5. How many values I have? There are 16 values. Okay, starting from 0 until 1.5 with a step of my step size is 0.1. Okay, so if I have analog value 0.44 volt, what is the quantized value? That means what is the output of the quantizer? Okay, if I have 0.44, Then what is the next level of the quantizer? Remember, the quantizer has steps 0.1. So 0, the first step, the next 0.1, 0.2, 0.3, 0.4. The next one is 0.5. So from 0.44, when it comes out of the quantizer, it will become 0.5. And I am representing with 5 bits. So this will correspond to 0101, which is number 5. Okay, so the minimum value is 0. 0.1 will be 0001. Okay, and 0.2 will be 0010, and 0.3 0011, 0.4 0100, and 0.5 0101. Okay, this way we quantize it and we change it to binary. As I said, when we do quantization, we have approximation errors. And usually if we have a large step size, okay, if our step size is large, then the error will be large, okay? So that's why we need to select appropriate step size. It's important to decide the number of needs for bits needed for satisfactory performance. The large step size means large jumps, and it causes significant errors between the actual value and its approximation value, okay, the quantized value execute. Okay, a small number of bits produce large step size. So if we increase the number of bits for the analog to digital converter, then the quantization step will be smaller. So the number of bits, if we have smaller number of bits, then we have large step size. And large step size will introduce a lot of errors. That means a lot of approximation error, or we call it quantization error or quantization noise. As a result, there is a parameter called signal to quantization noise ratio. Okay, so the signal power to the quantization noise ratio depends on the quantization noise. See, so if the quantization noise is smaller, then the signal to quantization noise ratio will become bigger, which is good, better. But if the quantization noise is large, then the signal to the signal power to the quantization noise ratio will be smaller, which is not good. Another error called clipping errors. So when is clipping error occurs? If we have a quantizer and the range of the quantizer is below the maximum of the analog signal. Okay, that means the range of the quantizer is not adequate for the input analog signal. For example, if I have a quantizer and the maximum value is 15 volt, but if I have analog signal, input signal of 20 volt, what will happen? The quantizer will clip it. Any value above 15 volt will be 15. If it is 16 volt, it will be 15. If it's 17 volt, 15. So this, we call it clipping error. Okay? In contrast to constant amplitude signals, setting the quantizer range for variable amplitude signals such as music is not trivial, because these signals, music and other signals, the maximum value is not, it's difficult to know the maximum value. Okay, it cannot be constant every time, so it's changing this time. That's why. If an analog signal has values beyond minimum value and maximum, the quantizer then clips it. Okay, any value below the minimum value of the quantizer will be clipped to Vmin. Any value above the maximum value of the quantizer will be clipped to Vmax. It's always difficult to get an appropriate step size for time varying signals such as speech and music. This is what we said earlier. However, from experience, there will be an acceptable trade-off between quantization error and clipping effects by adjusting the quantization level as follows. So if I have any analog signal X, such as music or speech, normally the quantizer will have a maximum value 4 times the RMS value of the analog signal. XRMS means the RMS, root mean square value. Okay, the root mean square value. So 4 times the RMS value, and the minimum value of the quantizer will be minus 4 times the RMS value. This is an accepted range in many commercial applications. Therefore, what is delta? The step size. The step size is maximum minus minimum divided by 2 power of b minus 1, the number of steps. Okay, the number of steps minus 1. Okay, this is delta. 8 times x RMS, the RMS value of the speech or the music signal, okay, the analog signal. How we get 8 times this? Because delta, the step size, is the maximum minus the minimum. So 4x RMS minus minus, it will be plus. So 8 times x RMS divided by the number of steps minus 1. Okay, so 2 power of b minus 1. Okay, consider the music recorded on audio CD. The music is measured to have an average voltage level of 2 volt RMS. Okay, so the music is 2 volt, the RMS value of the music is 2 volt. To avoid significant clipping, the quantizer range is set because we have here 2 volt RMS value. Then what will be the maximum? The maximum is 4 times x RMS. So 4 times 2, 8 volt RMS, and the minimum minus 4 times 2, which is minus 8 volt. So with each quantized sample represented by 16 bits, what is the number of steps? The number of steps of the quantizer, 2 power of 16. 2 power of 16 is 65,536. The step size, what is the step size? Delta is 8 times x RMS, the RMS value of the analog signal, minus divided by 2 power of b minus 1. So this is 16 divided by this minus 1, which is 244 microvolt. So the step size for this recorded music signal, audio signal, is 244 microvolt. This means. Okay, how do we hear a replica of the music stored in a collection of bits in a memory? That means, for example, if I have a music in a CD, how I can hear the music again? Okay, of course, we will have a CD player, for example. So CD players have what we call digital to analog converters. Okay, so in order to hear the original signal, we need to have a digital to analog converter. The digital to analog converter reconstructs the analog signal from the digital samples. It is a synthesizer. Okay, like if we have data, okay, digital data, we again get the analog signal from the digital data. That means, so we are synthesizing the original signal, making the original signal from the digital samples. The digital to analog converter produces a pulse whose amplitude corresponds to the binary value stored in memory. Okay. Now, in the digital to analog converter, again we will have staircase. So staircase means if I have a certain sample, we hold it for the duration of the sampling period, and we keep it. And then if we have another sample, again we keep it, and so on. So we will have pulses. Okay, we'll produce pulses for each binary or digital sample. So a separate pulse is generated for each binary value in the memory, and it lasts for the duration of the original sampling period TS. When plotted over time, these pulses provide a step-like approximation to the original analog signal. So we can see this in this graph. You see here, for example, if I have a certain digital value, that value at this point I will hold it until the next sampling time, and then at this time I will hold this sample until the next time. At this time I will hold the next, and so on. So I will have this kind of a staircase approximation of the original signal, the reconstructed signal from its digital samples. So note that if the sampling time is smaller, of course, we'll have a better approximation. For example, if you see this, what does this signal look like? It looks like a sinusoid signal, okay? So from its samples, digital samples, we generate these pulses, and this means an approximation of the digital signal when we are converting to analog signal. So if we, of course, minimize the sampling time, we get better approximation. However, it will be, we need more memory to store the data, because reducing the sampling time means I will have many samples per second, and then that means I need to have enough memory to store the data. Okay, this is how digital to analog conversion is done. Okay, now we summarize this chapter. Okay, we studied analog to digital conversion and the process, and the first step in changing analog signal to digital is sampling. Sampling means changing a continuous time and continuous in time and continuous in value signal to discrete in time and continuous in value. And then the next step is quantization. Quantization means changing the continuous value signal to discrete value signal. Okay, digitization, that means, and then changing it to binary finally. Okay, then we accomplish analog to digital conversion. But when we are doing analog to digital conversion, we have what we call quantization error. Why? Because we are approximating the original sample value to a certain specific allowable digital value or binary value. So when we do that, we introduce error. For example, if it is 2.6, and if I have a quantizer with integer values, and the next value after 2.6 is 3. But the original signal is 2.6, and when it comes out of the quantizer, it is 3. So what is the how much is the quantization error? 3 minus 2.6, 0.4. So I have a quantization error. So when we do quantization, there will be quantization error. But how can we reduce the quantization error? By increasing the number of bits, okay, used when we do from analog to digital conversion. Okay, increasing the number of bits means reducing the quantization step. So when we reduce the quantization step, the quantization error will reduce. And the other error is clipping error. A clipping error occurs when we have analog signal out of the range of the quantizer. The quantizer has a certain minimum value and a certain maximum value. When we have an input to analog digital converter which is out of this range, what we call clipping occurs. Okay, For example, if I have a signal of 12, but my quantization level is between 0 and 10, then if the amplitude of the input is 12, then it will be clipped to 10. So any value above 10 will be clipped to 10. And any value below 0 will be clipped to 0. This is also clipping error. Okay, and after we do the analog to digital conversion, and if we want to reconstruct the original signal, we have on the other side the digital to analog converter. This is, for example, in CD players. Okay, so in many devices, in mobile phones or many electronic devices, they have both analog to digital converter and digital to analog converter. So the digital to analog converter converts the digital values back to the original analog signal. With this, we have a brief introduction about analog to digital converter and digital to analog converter. Please see the examples again. Read the lecture notes for further understanding. Thank you for listening to this lecture.